Okay, so we are going to go through the example of 2.6. So the problem says, consider steady state conditions for one-dimensional conduction in a plane wall having a thermal conductivity of K equals 50 watts per meter Kelvin and a thickness L equals 0.35 meters with no internal heat generation. Determine the heat flux and the unknown quantity for each case and sketch the temperature distribution, indicating the direction of the heat flux. And then this is the chart with each of the cases. So just to start off, we're going to just start off with the givens. So they give us three things. First, they give us K equals 50 watts per meter Kelvin. They give us L equals 0.35 meters. And then they also give us the chart of T1, T2, and dt dx. So what are we looking to find here? We are looking to find the missing table values and Q conduction. Okay, so kind of going through our assumptions. We are going to assume first that it is steady state as it is said in the problem. We're going to assume no heat generation, again, because it's stated in the problem. We're going to assume 1D conduction in the x direction, again, because it's stated in the problem. And then because they give us a K value, we're going to assume constant isotropic properties. Okay, so next we're going to go over our governing equations. And I think just like a little picture will kind of help us with this. So similar to the picture that is kind of given in the problem, we have T1 here, we have T2 here. This is the length of L. And then we are just going to assume that the heat flux goes from T1 to T2. And we'll just assume this for each case so that the math then just takes care of the negative signs. And so from this, we know that it is conduction. So we are going to be using Fourier's law, which is Q conduction equals negative K dt dx. And again, because it's 1D and we have a set length, this is where dt dx equals T2 minus T1 over the length L. And again, we're going to keep it this way and always assume that conduction is going from T1 to T2, just so all the negative signs and everything works out. Okay, so let us start. Add another page. Let us start with case 1. So you can see from this chart up here, we can just add a conduction chart, and that would be in watts per meter squared. So you can see we're giving two things. We're giving T1 and T2 for this one. So T1 is 50 degrees Celsius and T2 is negative 20. So for this one, we will start with drawing our picture. So we can clearly see that T1 is greater than T2. So this is going to have a negative slope or a negative dt dx. So we can draw this as T1, T2, and it'll have a negative slope. And again, just so the math works out, we're gonna draw that like that. So first we will solve for Q conduction, the heat flux equals negative the 50 watts per meter Kelvin. And then T2 minus T1, so that was negative 20 degrees Celsius minus 50 degrees Celsius over the length 0.35 meters. And for this example, and also just in general for the examples here, we won't have to convert any of the temperatures to Kelvin because it is the difference between the two. And because converting from Kelvin to Celsius or Celsius to Kelvin is only a difference of 273.15. Any difference, the difference between two Celsius numbers or two Kelvin numbers, temperatures will be the same. So when we're doing the math, the Celsius and the Kelvin will basically cancel out because it's a difference between them and it's not just a temperature. And so when you do the math on this, you get Q conduction equals 1,000 watts per meter squared. And if you look at this picture, this makes sense because heat is going in the positive x direction. We can draw that quick. Heat is going in the positive x direction from T1 to T2. So that does make sense. And then dt dx equals T2 minus T1 over L, which equals negative 20C minus degree C, 0.35 meters. So dt dx equals negative 200 Kelvin per meter. And again, this makes sense because we're going from a higher temperature to a lower temperature in the positive x direction. So that would be a negative slope. So we can just fill in our chart up here. That was negative 200. This is 1,000. Okay, so moving on to case 2. So looking back at this chart, so again, we are given T1 and T2 again. So T1 is negative 30 and T2 is negative 10. Degrees Celsius. So again, we're going to draw a picture. And so here, we're going to draw it in the same way we were drawing it before. We're going to draw the heat transfer going from T1 to T2, but this time we're going from a colder temperature to a hotter temperature. So there will be a positive slope here. So we're going to draw T1 down here, T2 down here, be a positive slope. And again, just drawing this in this direction, just so the math all works out. So if we solve for the heat flux equals negative K, which is the 50 watts per meter Kelvin, and then it would be negative 10 degrees Celsius minus negative 30 degrees Celsius. Those negative signs will cancel out, divided by 0.35 meters, the length. And again, we don't need to convert this to Kelvin because it is a difference between temperatures. So then when you get Q conduction equals a negative 285.7 watts per meter squared. And so this being negative makes sense because we drew Q conduction in the positive x direction, but heat is actually being transferred from T2 to T1. So it's actually going in the negative direction. But so this being negative does make sense. And then if we solve for dt dx, you get negative you do negative 10 degrees Celsius, again, negative 30 degrees Celsius divided by 0.35 meters, and dt dx equals 7.1 Kelvin per watt. Oop, I put the wrong. I don't know if I put the wrong. Sorry, that is Kelvin per meter. My bad. And again, this makes sense with how we drew it because T1 to T2, we're going from a negative to a positive, and that is a positive slope if we draw Q conduction, and if we draw the picture in this way. So we can go and fill in our values up here. Okay, so for case 3, we have T1 is 7 degrees Celsius, and dt dx is now given rather than T2, and that is 160 Kelvin per meter. So go case 3. And so T1 equals 70 degrees Celsius, and then dt dx equals 160 Kelvin per meter. So when we're drawing our picture, this in the positive x, we have Q going this way. So we're drawing our picture. We have a positive slope, so that means we're going from a cooler temperature to a hotter temperature. So we will draw T1 down here. Again, we have a positive slope, so it has to be a positive slope. And we'll have T2 up here. So first we'll solve for we'll solve for T2. So I'm going to use dt dx equals T2 minus T1 over L. And then when you work that out and do the math, T2 ends up equaling dt dx times L plus T1. So then T2 equals 160 Kelvin per meter times 0.35 meters. And you see that the meters will cancel out and you'll just get Kelvin. Which again, because of the differences, it's actually, it can be just Celsius plus the 70 degrees Celsius. So you get T2 equals 126 degrees Celsius. And again, this Kelvin is a difference in Kelvin. And so because it's a difference, it can also just be Celsius. And then, yeah, so 126 Celsius, this is greater than 70 degrees. This makes sense with our positive slope. And so then if we do our Q conduction, we get negative 50 watts per meter Kelvin. I'm running out of room. Move this over. Times the 160 Kelvin per meter that we are given. We get Q conduction equals negative 8,000 watts per meter squared. And this is a negative number. And again, this makes sense with how we drew our graph. We drew Q conduction going in the positive X direction, but heat transfer is actually going from T2 to T1. So it's in the negative direction. It's a negative Q conduction. Let's add our values up here to our little chart. So we have 126, and then we have negative 8. So for case 4, we are now given T2 rather than T1, and then again, we're giving dt dx of negative 8 Kelvin per meter. Let's add another page. We'll do case 4. And so for case 4, we're again given T2, which equals 40 degrees Celsius, and then dt dx, which is negative 80 Kelvin per meter. So we'll draw a picture real quick. So that is in the positive X direction. We're going to again do Q in the same direction, just so all the math works out properly. And so we're given T2, we have 40 degrees, and this is in the negative, this is a negative dt dx. So because it's a negative, we need to have a negative, that was really bold. you have a negative slope. So T2 is up here and T1 is over here. And so this makes sense because it's a negative slope, so the slope here has to be negative. So let us solve for T1. So again, I'm going to use, this is really bold. This back down to, so again, I'm going to start with the dt dx equals T2 minus T1 over L, one of our governing equations. And then when you do all the math, it is T1 equals T2 minus dt dx times L. So T1 equals 40 degrees Celsius minus negative 80 Kelvin per meter times the 0.35 meter. And again, we're not going to convert this Kelvin because this Kelvin is actually a difference. It is not 80 Kelvin, it is a difference of 80 Kelvin. Then you get T1 equals 68 degrees Celsius. And this makes sense with our negative slope. We want to start with a greater temperature with 68 degrees and then move to a cooler temperature of 40 degrees Celsius. And then we can solve for Q conduction, which equals that negative 50 watts per meter Kelvin times that negative 80 Kelvin per meter. That's a little messy. Kelvin per meter. And you will get, when you do the math, 4,000 watts per meter squared. So this is a positive number, and this makes sense because we're going in the positive x direction. We're moving heat from T1 to T2, and how we drew our arrow, it would be in that positive direction. So this makes sense. We can fill in our little chart. We got 68, and we got a positive 4,000. Okay, and then for our last case, it's similar to the case before, case 4. So we're given the temperature of T2, which is 30, and then we're given a positive dt dx, which is 200. So case 5. So again, we're going to start off by drawing our picture. Positive x direction. We'll again continue to draw Q in the positive x direction, so all the math works out with the negative signs. We were given T2 equals 30 degrees Celsius, and then dt dx equals 200 Kelvin per meter. So we have a positive slope. So we want the slope to be positive between the two temperatures. So that means T2 will be up here and T1 will be down here. So from this picture, because we have a positive slope, we're going from a cooler temperature to a positive temperature where the slope is positive. So we're expecting T1 to be smaller than T2. And then because of how we drew our Q conduction in the positive x direction, we're expecting it to be negative because heat will be transferred from T2 to T1. So if we go through the math, we'll start with solving. We'll use this same T1 equals T2 minus dt dx times L. So we'll get T1 equals that 30 degrees Celsius minus 200 Kelvin per meter times 0.35 meters. And T1 will equals negative 40 degrees Celsius. And this is what we expected because we want T1 to be less than T2 because it's a positive slope. And then if we solve for Q conduction equals negative 50 watts per meter Kelvin times the 200 per meter, you get Q conduction equals negative 10,000 watts per meter squared. And like we said before, we expected this to be negative because of how we drew our Q conduction in the positive x direction, but heat transfer is being transferred from T2 to T1 because heat moves from hot to cold. And then we can just finish filling out our little chart up here. So we get -40 and -10,000. And so this is the finalized chart. Thank you so much.